In 5.1, we want to find the inverse of a function and then look at ways of determining whether two functions are inverses of each other or not. So to get the inverse, remember an inverse means that the x and y's have been swapped. That's for whether it's an ordered pair or an equation. If we have the ordered pair 3, 7, the inverse of that is 7, 3. So to get the function such that every ordered pair of this function is an inverse of every ordered pair in another function, first of all, we put it in y notation. We change f of x to y. Then we replace y with x with y. So we change y to x and x to y. And then we solve this for y. So we want to add 9 to both sides. And then to get y by itself, we divide both sides by 2. So we get y is x plus 9 over 2. In function notation, our original function was f. This is f inverse. So we use what looks like an exponent of -1, but it's really not meaning an exponent. We use this notation to refer to the inverse of the function f. So that formula would be x plus 9 over 2. So let's just make an observation. For the first function, if we put 7 in for x, we get 2 plus 7 is 14. 14 minus 9. That's an ordered pair that was f. If this is the inverse of f, then the inverse point should be a solution to this equation. Well, if we plug a 5 in for x, we would have 5 plus 9 over 2. That's 14 over 2, which is 7. So when we plug a 5 in, we get 7. And that's going to be true for every ordered pair. Any ordered pair that works for f, if we flip the x and the y, that ordered pair will work for this formula. Now, we're not really going to deal with one-to-one very much. The examples I give you will be one-to-one. We're more want to emphasize how do we get the inverse function. So here, let's get the inverse. Since I'm giving you this problem and ask for the inverse, then we are going to assume that this is one-to-one. So we put it in y notation. That's the first step. Then we replace every y with an x and every x with a y. Now we want to solve for y. So let's begin by getting rid of our fractions. To get rid of the y minus 7 on bottom, we multiply both sides by y. So those cancel. So on the right side, we have y plus 6. On the left side, let's get rid of the parentheses, so let's distribute x, y, and x times minus 7. So we have put in y notation. We've changed f of x to y. We swapped x and y. And now we're in the process of solving for y. So notice that y is to the first power everywhere we have a y. So in terms of the variable y, this is a linear equation. It's linear in y. So when we solve linear equations, we get that variable on one side, everything that doesn't have that variable on the other. So let's get all of our y's to the left. So let's subtract y from both sides. That will make those go away. On the right side, we have xy. Let's put our y term next, and then our 7x term, and then we're left with a 6 on the right. So both of these terms have a y. This term doesn't. So to get this term to the other side, so that only y terms are on the left, we do the opposite, so add 7x to both sides. So we get xy minus y equals, let's call that 7x plus 6. And the reason we get all of the y terms on one side is that that will give us a common factor. Every term has a y, so we can pull a common factor of y out. That leaves us with an x minus 1. And then to get y by itself, the opposite of multiplying is to divide. So divide both sides by x minus 1. So those cancel. So y is 7x plus 6 over x minus 1. In terms of inverse notation, f inverse of x is 7x plus 6 over x minus 1. So this is the inverse function if our function started out as that. So that function and this one are inverses of each other. At the point where we swap x and y, we have the inverse, but to put it in function notation, we have to have y by itself. And then once we get y by itself, then we can put in a function notation. All right. Now this problem asks us to use composition to show that f and f inverse are really inverse functions, that they're really inverses of each other. So if we take the composition of a function and its inverse, they will undo each other, giving us what we originally started with. So whatever our original input is, if we compose a function in its inverse, we get back to where we started. So let's suppose that for the function f, we had an ordered pair 5, 2. Then for the inverse of that, 2, 5 would be a solution. So just making up some numbers. We're not necessarily talking about these functions yet. So if I say find f of f inverse of 2, f inverse of 2 is 5. When we plug 2 into that function, the answer is 5. For this function that's just f, when we plug a 5 in, the answer to that is 2. Notice we just went in a circle. In this function, 2 gave us to 5, and then for the other function, 5 took us back to 2. And that will be true regardless of what our input is. If these functions really are inverses, this function changes that to something, this changes it back. So we can take two functions and we can show whether or not they're inverses by simply taking one function, plugging into the So f inverse is the function 6 over x plus 1. The function f is 6 minus something over that something. So we're inputting that whole expression. We're inputting the function f inverse into the function f. So in that function f, we're going to put 6 over x plus 1. 6 over x plus 1. So this input into that function. Now there are a couple of different ways that we could go about doing this. Since we only have one fraction on bottom, we could keep change flip. We could multiply the top, we could take the numerator and multiply it by the reciprocal of what's on bottom. Now, probably what they're going to describe doing, and the way they describe it is a little confusing. Another way of clearing improper or complex fractions is to get rid of the denominators. So if we had this x plus 1 gone and that x plus 1 gone, this would no longer be a complex fraction. So the opposite of dividing is to multiply. So we're going to multiply the top and the bottom by x plus 1. So this might be some algebra that you haven't done in a while. So we're going to do the first term times x plus 1. And then we're going to do the second term times x plus 1. And then the bottom, we're going to do the bottom times x plus 1. And notice by doing that, this x plus 1 on bottom and that x plus 1 cancel. This x plus 1 on bottom and that x plus 1 cancel. If we get rid of these parentheses, we would distribute and we would get 6x plus 6 minus 6. And on bottom, we would have 6. Well, 6 minus 6 makes 0, so 6x over 6. The 6's cancel, and we're left with x. So when we did the composition of a function and its inverse, we got x. So if they are really inverses, that will happen. That will always happen, that essentially does cancel if two functions are inverses. Now, this should work in either direction. If we put the inverse on the outside and put the other function on the inside, when we plug this function into that function, we should get x. So this one asks us to make a graph. So to make a graph, if we don't know exactly what it's going to look like, we need to make a table. We need some ordered pairs. So for convenience, these 5 ordered pairs. Some numbers to the left of 0, some numbers to the right of 0, and also 0. So if we plug a 2 in, we would have y equals 2 to the second. Well, 2 to the second, 2 times 2 is 4. If we put in a 1, we would have y equals 2 to the first, which is 2. 2 to the 0 is 1. If we put a negative 1 in, 2 to the negative 1 is the same thing as 1 over 2 to the first, so 1/2. 2 to the negative 2 is the same thing as 1 over 2 squared, or 1/4. So we can plot that. So at negative 2, we're at 1/4. At negative 1, 1/2, 0, 1, 1, 2, and 2, 4. As we go to the right, our graph is getting steeper and steeper and steeper. But as we go to the left, we're not actually going to cross the x-axis. We actually have a horizontal asymptote there. If we think about plugging in a number like negative 10, if we try to find y when x is negative 10, that's 1 over 2 to a big power. That's going to give us a really, really small amount, but it's still going to be positive. And that's going to be true whether that's negative 10 or negative 100 or whatever. If we have a negative exponent, that actually moves it to the bottom. That quantity is positive, that's positive, so we get a positive answer. But as this number gets more and more negative, this gets bigger and bigger, so this is getting closer and closer to 0. So we have a horizontal asymptote at the x-axis. So when we graph exponential functions, we have horizontal asymptotes. If there's not a number added to it, then our horizontal asymptote is at 0 at the x-axis. And instead of memorizing if our exponent is positive, our function goes one way, if it's negative, it goes another way. When is it flipped upside down? Just make a table and try to correctly use the order of operation once we get a list of points, we can plot those, and that will give us a good idea of what our graph should look like. Let's do this one. If we put a 2 in, 5 to the second is 25 plus 2. If we put a 1 in, 5 to the first is 5 plus 2. 5 to the 0 is 1. 1 plus 3. 5 to the negative 1 is 1 over 5 plus 2. Well, 1/5 as a fraction is 0.2 plus 2, so this would be 2.2. 5 to the negative 2 plus 2, that's 1 over 5 squared. That's 1 over 5 squared. 5 squared is 25. As a decimal, that's 0.04, so this would be 2.04. That plus 2 gives us our horizontal asymptote. So if we try to graph this, we have a horizontal asymptote at 2. And then if we plot those points, we get 0, 3, 1, 7, and 2 was out of the top. Negative 1, 2.2, negative 2, 2.04. So that starts getting steep in a hurry. So that's an exponential function. And it's not going to cross that horizontal asymptote. Our horizontal asymptote is y equals 2. Let's do one of these where we have compounded interest. So our compounded interest formula is A equal P times 1 plus R over N to the NT. So P is the principal, or your starting amount. R is your rate, which is your annual percentage rate. So if it says 6%, that means 6% annually. Now, if it's 6% annually, that doesn't necessarily mean you get 6% interest every single time. That just means your total annual rate is 6%. Here, we're getting interest semi-annually. So in that case, N is 2. That's how many times we get interest a year. If it were quarterly, N would be 4. If it were monthly, N would be 12. So A is the current amount, or the amount after time t. And t is time, usually in years. So for hours, our principal is 2,000. 1 plus R is 6%, which 6% as a decimal. If we go from percent to decimal, we move our decimal 2 places to the left. So 1, 2, 0.06. N is 2, so 2 on bottom. N times T is 3 years, so 3. And then instead of N, we know N is 2. So order of operation tells us that we're going to do what's inside parentheses first. So that's going to give us 0.03 when we divide. Let's talk about what that 0.03 is. We're getting interest twice a year. So instead of getting 6% both times, we're going to get 6% divided by 2 both times. So we're going to get 3% twice. Well, guess what 3% twice is? 6%. if we were getting 6% quarterly, or 6%, and we were getting interest quarterly, 6% divided by 4, that's how much we would get each quarter. So not the whole 6% every quarter, but a fourth of that every quarter for a total of 6%. The good thing about that is that once you accrue interest, that gets added to your total, and then next time you get interest, it's not only what you started with, it's what you started with plus the interest you've already gained. Now we can go ahead and multiply this exponent, 2 times 3. 6, that's the number of times interest is accredited. Twice a year for 3 years would be 6 times. So on the inside of that parenthesis, we get 1.03. After we do parentheses, we have to do exponents. So we're going to do 1.03, raise that to the 6th power, and we can write that number down. I'm going to keep that whole thing in my calculator as I'm doing my calculations, but we can call that about 1.19. But I'm going to take the whole value in my calculator and multiply that times 2,000. So our amount after 3 years at this interest rate compounded semi-annually is $2,388.10. So if you're thinking about it as an investment, if you invest $2,000 at 6% interest compounded semi-annually for 3 years, this is the value of your investment after those 3 years. If you think about it as taking out a loan, this is the amount that you would have to pay back. If we want to talk, if we consider this an investment, the interest that we earn is the difference from our amount at the end minus what we started with. So we end up with $2,388.10, and we started with $2,000, so that means we gained $388.10 of interest. If you're borrowing money, if you were the one borrowing the money, that's how much interest you would have to pay for borrowing the $2,000. But if you're the investor, then you've made $388.10 for investing your $2,000. So the biggest thing is knowing what our formula is for compounded interest. This is for compounded interest or compounded growth. Know what each variable stands for. Make sure we convert percent to decimal and then do order of operation.